Hey, before I get back start into ramps, the next topic, a couple questions that came in last time. The move of websites messed up my messaging system. Is running again now. So let me address it. So these relate to balls, falling balls. And so the first question is, if you toss a ball up, is it not experiencing the force of a push in addition to its weight? And the answer to that is yes. During the throwing it up, absolutely. There is a second force on it, the force of my hand on the ball. That's what's causing it to accelerate upward. I'm basically overwhelming the downward force of the weight of the ball. So the net force on the ball is upward. It's accelerating upward. So while it's touching my hand, it is accelerating. There is an upward force on it. Okay? Once it leaves my hand, the story changes. And it was my mistake not to make it clear that the story doesn't start until the ball leaves my hand. Once the ball is out of my hand, I'm no longer pushing on it. So there is this sort of, not instinctive, but intuitive, historical way thinking that if you threw it and then it's continuing to go upwards, somehow you're continuing to push up on it, somehow. That's mythological. There really is no upward force on it once it stops touching you. And so that's a misconception that's easy to have because Aristotle had it. That somehow you push it, it keeps on going because you're continuing to influence it. It's not true. So in general, I got to be careful with my stories, sort of when they start and stop. Sometimes I make it unclear what I'm covering. In this case, only the part where the ball was free of my hand, in which case it's a true falling object accelerating downward under the influence of the only force it's experiencing, its weight. The other question is another important one that comes up all the time. Over the years, has come up many times. At the peak of the ball's travel, so right now, right, is way up before it's starting to come down. Right at that peak, isn't the ball's velocity zero, meaning that its acceleration is zero? And the answer to that is yes. The ball's not careful. Qualified yes. Yes to the first part. At that peak, the ball's velocity truly is zero. If you think a moment earlier, it was heading upward. If you think a moment later, it was heading downward. It's in transition across that zero. Not up, not down. So, yep, there's an instant in time, and it's truly an instant, when the velocity is zero. The idea that you can have a velocity of zero for an instant may be troubling to you, but you can, and you've played with calculus. For me, it's play, I guess. You may go like struggle or suffered. With calculus, you know that curves go through things, and there are moments that there really are moments of a value. Not the value isn't the same a moment before, a moment after. It's a value right now, and that's true of velocity. It's momentarily zero. That does not mean it's not accelerating. In fact, it's accelerating downward at the famous acceleration due to gravity. It's a falling ball still. So right at the top, it is in the process of changing its velocity more and more downward. That's why it goes from heading upward a moment earlier to heading downward a moment later, because it was changing its velocity and it just swept through zero just for an instant. Other questions about those ideas? It may take a while to wrap your head around it. At the top of something's flight, a falling object is still falling. It is still accelerating downward at the acceleration due to gravity. The only thing special about it is there is a moment when it's motionless. The last question was an interesting one. I talk, again, units. I don't talk about them all that much because we can get lost in them. I can get lost in them. And so most of the world has adopted this System International, SI, or also called the metric system, for measuring everything, and that's great. It has the simplicity of all the units are properly interrelated. That is, that a force of 1 Newton exerted on 1 kilogram of mass causes 1 meter per second squared of acceleration. They're elegantly interconnected. The other system, the one we use, and what to call it, apparently it's, at least in part, is the British imperial system. Well, the empire has come and gone, and we're still left with a lot of the units of that system. So is England and Great Britain. They've moved farther away from it than we have. We're still mired in it. There is the problem that many things that you have around the house have dimensions in inches and stuff like that. Like if my laboratory is filled with inch-dimensional nuts and bolts and stuff, as well as metric nuts and bolts, and you can't interchange them. It's, it's painful. You can just live with it. In any case, the metric unit of mass is one I never use, so I forget. I had to look it up again. It's called the slug. It is the mass that when you exert 1 pound of force on something, it accelerates at 1 foot per second, and foot per second squared. It's a little under 15 kilograms. It's a wacky unit of mass. We don't use it. That's one of the very, very few metric units that we have sort of universally adopted. It's the kilogram. Slugs are for garden pests, although they're kind of friendly too. Any other questions? Yeah, the University of California, Santa Cruz has as their mascot's the banana slug, so they're a unit. Banana unit. All right. Topics. The next topic to go on to is ramps. And before I put a wagon on a ramp and talk about what's going on there, let me start by asking a question here. So I'm going to put this guy up here. Dun, 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 it's there, yay. Again, those of you who have eye clickers, great. If you don't eye clickers, great. Answer the question in your head. It's nice to sort of see what the general thinking is. It's biased by the people who own eye clickers, but whatever. So the question at hand, I haven't started, I guess, is what force is the table exerting on the ball? So the ball I have in mind is this big red ball here, and nobody's touching it. It's just the ball and the table in this story, and actually this story will come up more than once. So just the ball and table. My hands are off. And the question is, what force is the table exerting on the ball? See what you think. All right, we'll go to the 30-second point and call it. And in general, you're always welcome to discuss this with people around you. All right, 5, 4, 3, 2, 1. Okay, the great majority of you are going for, it's a force, the wording is a little bit complicated, right, what I do. An upward force equal in amount to the ball's weight. Why all the words? That is the answer, okay? Which is great, okay? Why all the words? Because the ball's weight is in the downward direction. So I have to rip out the direction part and talk about the table pushing upward with a force just as strong. And just as a little aside about vector quantities, which force is, there's the amount, there's the direction. The fancy name for the amount, setting aside the direction, it's called the magnitude of the vector. I usually call it the amount. And the direction part, not surprisingly, is called the direction. Okay? So we had to take the amount part out of the weight of the ball and flip it upside down and make an upward force. If I leave out the in amount in some of my questions, forgive me, it gets wordy to keep saying equal in amount to the force. This force, that direction, is equal in amount to that force, that direction. Just a lot of words. Okay? Back to the question, though. And you all got the answer. The upward force is equal in amount to the weight of the ball. How do you know that? Is there, it's not legislated somewhere. you can observe something that tells you the net force on the, I say the answer, why don't I? That the upward force on the ball is equal to the, in amount to the weight of the ball, opposite direction. What's the glaring effect that you see that tells you that those forces are equal but opposite in amount? Cooper. The ball's not moving, and even more important, the ball's not moving, which tells me the velocity is zero. What else is going on about it? Is the velocity changing? No change in the velocity. It's a constant velocity of zero. So the ball is experiencing what net force? Zero. So that, which I said by accident moments ago, it's experiencing zero net force. We know that because the ball's motionless and staying motionless, which is the same as saying it's equivalent to saying its acceleration is zero. So we know the table has to be perfectly canceling the ball's weight. And so I often ask questions like, questions on the exam will be like, what force is the table exerting on the ball? And in some classes you would calculate the ball, there would be numbers all over the place. In this case, the answer is a quantity that has a very specific value. It's better than the longest number you could ever write. More accurate, 1.0000000. It's an upward force exactly equal in amount to the ball's weight. I don't care what the ball's weight to 30 decimal points is. It's equal to that amount. Okay? So named quantities are great. And we know that the weight down, the table's force up, are equal in amount because the ball's not accelerating. Okay. Another question. Oh, it's already up there, right? What do I know? Okay. Subtle change. What force is the table? Oh, what happened here? Oh, no, I got it right. I've got two different displays. What force is the ball exerting on the table? We've flipped the roles. You okay with the question? Any questions about the question? We'll go to 30 seconds here. No, 5, 4, 3, 2, 1, 0. Oh my God. You're all, excuse me, I was writing this. Oh. Oh. Is this going to work? Yeah. I changed it too subtly. There, try this one again. No. I changed it. What happened? Did I change the wrong one? Yeah, of course I changed the wrong one. I damaged my first one, but that's okay. All right. You okay? This is a better question. You guys are too silent. Like, you should say, like, hey, wait a second, the question's wacky. All right. Don't, what is it called? Don't trust authority or something like that. Like, be skeptical. I make mistakes. Okay, try this version. Oh, I'm happier with the results this time. All right, 3, 2, 1, 0. All right. This is much better. Okay, B, a force equal to the ball's weight. It is, which is great. And I could have added in that question, I could have added the choice that the ball's weight, the point is, where I'm going, the point of it is this. The ball is indeed pushing down on the table with a force that's identical in amount and direction to the ball's weight. It is not literally the ball's weight. That's what I wanted to say, is that the ball's weight is what the Earth exerts on the ball. It's truly the ball's business. What the ball is doing is it's somehow managing to push down on the table just that hard. And how do we know that? And the way we know that involves another observation about the universe, and the last of Newton's laws. And it's called Newton's third law. And it's the famous action-reaction law, which is used carelessly all over the place and stuff. This is the real meaning of the law. And that is that if that ball, if the table pushes on the ball with an upward force equal in amount to the ball's weight, we know that. I'm giving you the third law in context, which is for better or worse. There's an upward force on the ball equal in amount to its weight. The ball has to push back in the opposite direction with exactly the same amount of force. Namely, it pushes down on the table with a force equal in amount to the ball's weight. And that's a striking universal character of our universe. Yeah, please.
So the ball's weight is not a force?
The ball's weight, the question is the ball's weight not a force? No, the ball's weight truly is a force. It's a force on the ball. The ball, however, is able to exert a force on the table also, which I've got to come back to. How is it doing? It's not a gravitational force. It's a force that I call a support force. It's not gravity. But that downward force of the ball on the table is a certain push. And it's straight down and it's a certain amount. It happens to be exactly the same as the Earth's force on the ball. They're two separate forces. Is that okay with everybody? The Earth pulls the ball pushes on the table. Those are two different forces. So let me take a second and talk about what kind of force these two forces are. They're not gravity. Gravity is this one that reaches out from effectively the whole Earth, essentially effectively at its center, and pulls down on us, attracts us to the Earth. In fact, and gravity is universal in the sense that everything exerts gravitational attraction to everything else. So you all are pulling towards each other a little bit too. It's very weak. If I had a knob and I could slowly turn it up, you'd all clump together. You'd accelerate towards each other and it would be a problem. It might be fun briefly. And then this force is a different force. This semester will go on into the world of electricity and magnetism and stuff. And actually the force involved between the table and the ball involves to some extent electricity and magnetism at a very tiny level. You don't notice it as being electricity and magnetism, but okay. I call it a support force. You may have heard it with other names, normal force or contact force. And they're all the same concept. They're all it's a simple concept that two objects do not like to occupy the same space at the same time. So if you try to push your right hand into your left hand and have them be in the same place, the surfaces push apart. It's the overlapping of atoms and molecules and all that stuff. And that pushing apart is directly away from surfaces, perpendicular to surfaces, a term I hope you're familiar with. The support forces that this horizontal table can exert are strictly vertical, no other direction. Forces along surfaces will come to later. Those are known as frictional forces. This is the support force, and if this heavy object here, the cube, the reason when it tries to occupy the same space as the table says and it pushes straight away, perpendicular to its surface. In this case, straight up on the block, and the block, seeing the table trying to occupy its space, pushes straight down on the table. So those are support forces. It's okay? So the ball and table are exerting support forces on each other, even though the ball is round. Right at the very bottom of that ball, that curve at the bottom of the ball, it's exactly horizontal right at the point where it touches the table. So it's pushing directly away from its surface, perpendicular to its surface, normal to its surface. These are all mathematical concepts. Directly away, which is straight down. It's pushing straight down on the table. And so that's the world of the support forces. The other thing I introduced is this Newton's third law idea, that if one object pushes on a second object, A pushes on B, B pushes back absolutely without exception on A, equally hard in the exactly opposite direction. All right? That's the action-reaction idea. Any other interpretation of it is having fun with taking literary license or something. So to stare a little more at that notion of objects pushing back on each other, because it involves some non-intuitive stuff that you may go, I totally believe there's no problem, no problem. Let's check out the ways in which it's easy to get confused. First off, if you push on a friend, and is there any case in which your friend will not push back on you? You hear the question? Go for it. There you go. I'm ready to hear that. Smack, right. No, I didn't mean to. All right. All right, 3, 2, 1, 0. No is indeed the correct answer. There's nothing your friend can do to not push on you. If you manage to push on your friend, which is part of the issue, if your friend has run away, is like a mile away from you, it's going to be tough to push on them, so you're going to have a difficulty with the first clause in this question. But if you succeed in pushing on your friend will push back, whether they're asleep, whether they're running toward you, running away from you. Nothing of that sort matters. They'll push back on you, and the force they'll exert on you will be interesting. It's the same amount as the force you exert on them. I had some important thought I wanted to convey with this one. Oh, that this situation, I mean, your friend can be a statue. You love statues, I don't know. You push on the statue will push back. Well, this is very convenient for things like, suppose I'm standing here motionless, and I want to go over to the wall on the right. How am I going to get there? Well, I need to accelerate to the right to begin to start moving that way. I need a force to the right. How do you get a force? I can ask one of you all to come up and shove me, but it's easy. All I have to do is push something else to your left, and it will push back. It has to. It has no alternative. So I will push the floor to your left. I do it with my feet. I use the force of friction that we're not talking about yet. So I'm going to shove the floor to the left. Oh, it shoved me to the right. I accelerated. Now I can coast to the wall. And then I can have it stop me. Because again, the story ended when I stopped. I didn't want to keep going. I would be out in Bonnycastle with a good fall ahead of me. So I pushed on the wall and had to push back on me and accelerate me to a stop. All right? So we do this all the time. You get yourself moving around by pushing on things and having them push back, and every variation on that. A question can come up is the force that these things, potentially inanimate objects or human objects, the force they exert on you, how is that related to the force you exert on them? And so let's look at this question. If you push on a friend who is moving away from you, how will the force you exert on your friend compare to the force your friend exerts on you? Okay, so now there's some movement in this. See what you think with this one. 5, 4, 3, 2, 1. All right. The answer is C. They are equal in magnitude, that equal in amount. But the other ones are sure tempting. That you push harder, your friend pushes harder. So let's try that. I'm going to do this I need one volunteer for this. Can I have somebody who will come up and push scales against me? Please, Cooper, come on. All right, so here's the idea. These scales report how hard we're pushing on stuff. So, and it's in newtons because we're advanced here. So this is a 10 Newton push. So you take the scale and make it so people can read the dial. And I'll take this scale, and we'll start off. And so this will read how hard I'm pushing on you, okay. Cooper scale will read how hard he's pushing on me. And our first job is to see whether there's any situation which we can push with different amounts of force. Okay? So we try, a little bit. Do you guys ever see the two dials reading differently? It's a little hard to read in any great detail, but nothing we can do. Okay. Now let's start moving. Cooper, you're going to move away from me, and okay. Same trick. Now I'm going to move away from you. Okay. Now we're going to accelerate. Okay, thanks. Yeah, okay. You guys get the idea? Nothing we can do. The forces we exert on each other are always the same, whether we're moving toward each other, away from each other. I guess we should have done the back and forth. We seem to be moving together, but we could be crashing into each other. Every possibility, they're always the same. All right? That has non-intuitive pieces to it, because you kind of think like, well, if you're pushing on a bicycle goes by you, or a Tesla, okay? You reach out and you push on it, your push will be very gentle, right? Because it's going away from you so fast. Well, it's the fact that you have a tough time pushing on it when it's moving really fast past you. So your force is going to be small, typically. But that means the force back on you is going to be small too. They're still equal in amount in opposite directions. If something's coming at you, I don't know, somebody's running into you, or they're throwing a ball at you or something like that, your force is going to be very large, typically. And well, the force you exert on it's going to be large. The force it exerts on you is going to be equally large, opposite direction. They all go together. Questions about those ideas? Yeah, one of the questions came in about support. Are support forces the ones that are equal and opposite? And the answer to that is support forces do appear in pairs that are equal and opposite, but so does every other force in existence. So the support force that the ball exerts on the table to keep the table from going into the ball is equal and opposite to the force the table exerts on the ball to keep it from going in, the ball from going into the table. They come in a pair. But every other force comes. So the forces that we were exerting, which were, some of them were support forces, some of them were other things, they always come in pairs. And one of the mysterious pairs that will show up is this ball has a weight, right? It's a 16-pound bowling ball. That means the Earth is pulling down on this ball with a force that's straight down and 16 pounds in the American or imperial unit of force, right? What's the paired force to this? They come in pairs. So that was the Earth's force on the ball. What's the other force in the pair? The ball's force on the Earth. The ball is pulling up on the Earth with a force of 16 pounds straight up. It's there. It is truly there. You affect the Earth, yep. And if I throw the ball up, the ball is being pulled down and is therefore accelerating because of that downward force due to gravity of the Earth. And the Earth is pulled up toward the ball and is therefore accelerating up toward the ball as a result. That acceleration is real. It is exquisitely small for the Earth. Because why? What is it about the Earth that makes that acceleration so dinky? The mass. The Earth's got way too much mass to notice very much. But I remember as a kid asking my dad, Dad, when I'm jumping up and down, am I actually affecting the Earth? Am I causing the Earth to accelerate? The answer is absolutely. Yep. All right, so you can make the Earth accelerate. It's pretty dinky because the mass is pretty big. And there are issues about how the force actually affects, first it affects the floor, and then the floor affects the walls, and then the walls affect the ground. It's a long process, but you do actually affect the entire Earth. You have to. If these things weren't there, these effects weren't there, much of the structure of physics would just crumble. They're required to be self-consistent. It's like if you add 1 to a number, do you always get the next number in the integers? If you start with integers, yes. If there were one exception out there, 2,007,000, where you add 1 and it takes you to the second integer afterward, the whole number theory would crumble. Okay, so physics has to be self-consistent. You have to have these effects. Important thing to mention about Newton's third law, and the fact that forces always show up in pairs. Okay, there are a couple of things to mention. First of all, forces are always exerted between objects. And you ought to be able to identify both objects, at least in principle. So for example, the force, the upward force on the ball that's supporting it against falling, it comes from the table. So the table is exerting the force upward on the ball. Forces don't just appear out of nowhere or get carried with them. So when you see there's an asteroid streaking through space with tremendous force, that shows up in media. No, while it's streaking through empty space, it's not pushing on anything. So there's no force. It doesn't carry force with it. What's the object exerting the force on the asteroid? Well, none. That's the acid test for it. Nope, there's no force. It is carrying something with it that's in our future. It's carrying momentum with it, which is something you can carry. But you can't carry force with you. Force is exerted between objects. And where I want to go with this is a familiar, important misconception. Yeah, I'll put it up there for you to see. I think I've got it in the book as a misconception alert as well. This idea that two objects exert equal but opposite forces on each other mean that there are an awful lot of situations where there are two forces around and they happen to point in opposite directions and be equally strong. And that notion that there are two forces around that are equally strong, what if you add them together? They add to 0. And that means nothing. That means no acceleration, right? So we do indeed say in the case, well, I don't want to have the ball in it. You can pick a situation where two objects are pushing on each other. A person pushing a cart, and the person pushes the cart forward, the cart pushes the person backward, equal amounts in opposite directions. Those two forces truly are equal in amount and opposite in direction. If you add them, which is the key issue, why would you ever add them? Okay? But if you do add them, they will add to 0. And that makes it sound like there will never be any acceleration. The net forces will always be 0, and there will be no acceleration, and nothing will ever move, interestingly, and that will be the end of the world. Crunk. We'll all fall down and do nothing. Where's the problem in that thinking? Which many of you will think through 2 weeks from now. You'll go, and you'll try to remember back to this moment, and hopefully this will stick at least a little bit. The key issue here is, why would you ever add those two forces? Because the force of the person pushing the wagon is a force on the wagon and is the wagon's business. The force of the wagon on the person is on the person, is the person's business. When you calculate net force, it's always on the net force on an object. And so if you're going to calculate the net force on the wagon, you're only going to include one of those forces, the force of the person on the wagon. The force of the wagon on the person, that's not part of the sum. So if the person's force on the wagon is the only force acting on the wagon, it's going to accelerate. And if the the wagon in turn is pushing back on the person. If that's the only force on the person, ignore the one that's on the wagon. It doesn't matter. It doesn't affect the person. So the only force on the person, then the person's going to accelerate. So Newton's third law doesn't tell you anything about how objects are going to accelerate. It just tells you that forces show up in pairs on different objects. So you never sum the two forces. There's never any particularly useful reason to sum the two forces in a Newton's third law pair. Yes, it'll sum to 0, but it won't have any consequences that anybody cares about. All right? It's like adding up, I do analogies. I love analogies. So the weight of the moon and how much that pen weighs. Why would you add them? What context would that ever matter? All right? So, I really am leading up to how ramps work, but I'm taking we're on the sidewalk going very slowly towards the ramp, okay? So the question here this time is, can the ball ever push down on the table with a force greater than the ball's weight? And I will remind you the story only has the ball and the table in it at this moment, but I didn't restrict anything else. Those are two of the only objects we care about. I mean, the Earth, we do care the Earth's there because it's giving the ball weight and stuff, but I'm not involved, okay, at this moment. You okay with the question? See what you think here. Five, 4, 3, 2, 1. Interesting. So we got a pretty big, a split with the majority going for no. The ball can never push down with a force greater than its weight. Did I say anything about whether the ball was accelerating? And does that matter? I never restricted it. The ball might be allowed to accelerate. Try this one again, and keep in mind that the ball could be accelerating. Five, 4, 3, 2, 1, 0. You guys got it. Ooh, yes. The ball can indeed push down on a force with a force greater than its weight. In fact, it can push down with a whole variety pack. And so, now I'm going to have letters and numbers all over my head. I loved my sister's, one of my favorite stories was, I got to tell you anyway, was somebody giving a lecture like this. And he happened to have no hair. And he was there, and the number 8 showed up here. And someone said, anyone for some pool? All right. Okay. Anyway, right now, right now, how hard is the ball pushing on the table? Again, I wasn't really involved in it at that moment. 0, of course, right? So there's no problem in having the ball exert no force on the table. How can I have it exert a force greater than its weight? What do I have to do? Drop it. So instead of dropping it on drop it on the table. As soon as it hits the floor, hopefully I'll catch it before it gets to the floor. Ready? That was decent. It was a little scary, right? Let's try one more time. All right, I'm sure everybody in the front row is really happy to try this again. All right, it pushes down very hard. So I'm not going to do on the floor. But so there is no problem having the ball pushed downward on the table harder than its weight. It just has to be accelerating at that time. So when I had it just sitting there, which it's doing right now, it happens to be motionless and not accelerating. And that's the reason, given that, we know that the table is pushing up on it just enough to support its weight, so it's pushing down just enough with an equal and opposite force, so it's exerting a downward force on the table that is equal to the ball's weight. But it is not literally the ball's weight. This is the reason why that's important. The ball can push on the table as hard or as soft as it likes. The situation matters. If it does push down on the table really hard, the table is going to push up on it really hard, and it's going to be accelerating upward. So when I dropped it on the table, it got it up to develop a good downward speed. It then hit the table, moving down with a big downward velocity. The table said, you're not coming up. This is my space. I'm going to stop you from coming into the table. To do that, though, it has to push upward with a tremendous upward force to stop this falling object, this descending object. That upward force, effectively the sky's the limit. It depends on how fast the surface has to stop the impacting device. This is how hammers work. When a hammer hits a nail, if you just rest the hammer on the nail, motionless and staying motionless, as in no acceleration, the downward force that the hammer exerts on the nail is going to be equal to the hammer's weight. But if you get the hammer moving when it encounters the nail, and there's a brief period in which the nail has to push up tremendously hard to keep the hammer from basically occupying the same space, the two objects exert what are just commonly called impact forces, which no longer have anything to do with weight or very little to do with it. They're just basically how hard do these two surfaces have to push on each other to not overlap. And it can go astronomically high. And that's how a hammer can shove a nail into wood and things like that. That's why, for example, you try not to walk into cement walls, because you're going to be stopped very quickly by way of a huge impact force. It hurts. We'll see, and I'll do it more later, that you would much rather walk into a tapestry on the cement wall, which would slow you more gradually by way of a smaller force and a smaller acceleration. All right? So, a question came in: if there are three people pushing on one object, is that an instance where the forces do not come in pairs? And the answer is no. They're still pairs. There are now three people pushing on the ball, and the ball is pushing on three people. There are now 6 forces in the story. A pair from person A on the ball and ball on person A, and a pair from person B and the ball on person B, and a third one, okay? You can't get around it. Forces always come in pairs. And that'll happen in things as we go on. Over the years, I've talked so many topics. Which ones exactly will hit? I'm thinking a motor trying to turn its, or an engine trying to turn its rotating device exerts forces on that rotating device. The rotating device in turn exerts forces back in the motor. It can't help it. You twist something, it twists back on you. We'll see that the twists are very similar to forces. They have a different name and a different outcome. They're called torques, but they cause rotation rather than movement from place to place. But you can't get away from it. And this is, it shows up in a zillion contexts. I try to leave the military context out for whatever reason. But you all, any of you who've ever shot a rifle, know that it gets that bullet going forward like crazy. Well, there's a force forward on the bullet. The bullet, in turn, has to exert a backward force on the rifle, and it comes back at you very fast. And so my one episode of skeet shooting, 25 chances, now I guess it was a shotgun, but I was ready to stop after 25 because my shoulder hurt from getting hit by the shotgun coming back because the two pushed apart. It's unavoidable. Movies, they often leave out some of these physical things because movies, particularly CGI graphic stuff, is full of mistakes, things that aren't possible. It is not possible to blast some creature with this monster whoop-de-doo gun. You know, you go, poof, and the creature just goes flying across the room to, like, that means that the whoop-de-doo gun ultimately exerted tremendous force on the creature. There's a force going the other direction, and it's going to be on whoever is holding that blaster. They're going to fly the other direction, but they didn't in the movie because it wasn't convenient or whatever. Sorry, not physics, not our universe. All right, before I obliterate the entire time, let me start showing you where we're, go away, there we go. It's slow, computers are slow. Okay, so we're about to go on the ramp, and we're, you know, I'm lined up well for Monday here. Right now, it's not a very interesting ramp. It's got no slope at all, but we know how all of this works. There are support forces around. The wagon has a weight, and particularly with a heavy, blocky kid in it, and the sidewalk now is pushing up on the wagon to support its weight. We know how strong that upward force is. It's equal in amount to the weight of the wagon and kid. It's all good. Okay. What happens if I tilt turn it into a ramp? So let me do that. I'll make a gentle ramp so things don't happen too quickly. If I put the wagon and the kid on the ramp now, there are still support forces around because the wagon and the ramp do not want to occupy the same place at the same time. And their friction is not part of the story yet because I got wheels on the wagon. If I had no wheels on the wagon, friction would get involved. But right now, the only forces these two surfaces can exert on one another are perpendicular to themselves. And if I let go of the wagon, it accelerated. So something new showed up. When the ramp was horizontal, when it was a sidewalk, no acceleration, because the wagon was experiencing two forces. Its weight downward and an upward support force from the sidewalk. They were exactly equal amount, exactly opposite direction. They exactly summed to zero. Now I've got a problem. Having tilted the sidewalk into a ramp, those forces can't sum to zero anymore. And the reason they can't sum to zero is support forces, as I said, always point perpendicular to the surface. Normal, right angles, all those words are usable. Right now, because the surface is no longer horizontal, the support forces it exerts aren't vertical. They are up and to the left. When I have that, oh, I do have a stick. I happen to have a really long stick, okay? So this is what the direction in which the support forces that the ramp can exert point. It's not vertical anymore. So as a result, the downward weight plus the support force up and cockeyed, they can't sum to zero. You can't sum two forces, no matter what their strength are, that point in directions that are not opposite. You can't sum them to zero. It's not going to happen. You're going to have something left over. And the leftover that you have, in this case for the ramp, I just call it the ramp force. It's the imperfect cancellation between a weight straight down and a support force up and at an angle. When you put them together, they don't quite kill each other off. You end up with a little leftover, which happens to point exactly down the ramp, nicely enough, and it causes downhill acceleration. And this is you've lived that your whole life on, I don't know, tricycles, wagons, bicycles, your car when you're in neutral for fun and games, losing things down the hill by accident. And you know that force, and consequently the acceleration, gets stronger as the ramp gets steeper. So it actually evolves smoothly from zero ramp force when the ramp is exactly horizontal and is not really a ramp, to a really big ramp force when the ramp is vertical. At this point, the ramp force becomes the full weight of the object. And it's fractions of the weight of the object in strength all through the other tilts. Okay, so continue this sort of stuff on Monday. Have a good weekend.